The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so let's move on to our next topic. So here we have found things about lengths, angles, and stuff like that. One important concept that we haven't understood yet in terms of vectors is area. So let's say that we want to find the area of this pentagon. Well, how do we compute that using vectors? Can we do it using vectors? Yes, we can, and that's going to be the goal, but how? So the first thing we should do is probably simplify the problem. We don't actually need to bother with pentagons. All we need to know are triangles. Because, for example, you can cut that into 3 triangles and then sum the areas of the triangles. Okay, so perhaps easier, what's the area of a triangle? So let's start with a triangle in the plane. And, well, then we need 2 vectors to describe it, say A and B here. How do we find the area of a triangle? Well, we all know base times height over 2. So what's the base? What's the height? Well, so the area of this triangle is going to be 1/2 of the base is going to be the length of A, and the height, well, if you call theta this angle, then this is length B sine theta. Now, that looks a lot like the formula we had there, except for one little catch. This is a sine instead of a cosine. How do we deal with that? Well, what we could do is first find the cosine of the angle. We know how to find the cosine of the angle using dot product. Then solve for sine using sine square plus cosine square equals 1. And then plug that back into here. Well, that works, but it's kind of a very complicated way of doing it. So there's an easier way. Okay, and that's going to be determinants. But let me explain how we get to that, maybe still doing elementary geometry and dot products first. So let's see. What we can do is instead of finding the sine of theta, well, we're not good at finding sines of angles, but we are very good now at finding cosines of angles. So maybe we can find another angle whose cosine is the same as the sine of theta. Well, you've probably heard about complementary angles and how, if I take my vector A, I have my vector B here, I have an angle theta. Well, let's say that I rotate my vector A by 90 degrees to get a new vector A prime. Okay, so A prime is just A rotated by 90 degrees. Then the angle between these two guys, let's say theta prime, well, theta prime is 90 degrees or pi over 2 radians minus theta. So in particular, cosine of theta prime is equal to sine of theta. Okay. So in particular, that means that length A, length B, sine theta, which is what we would need to know in order to find the area of this triangle, is equal to, well, A and A prime have the same length. So let me replace that by length of A prime. Okay, I'm not changing anything. Length B, cosine theta prime. And now we have something that's much easier for us, because that's just A prime dot B. Okay, so that looks like a very good plan. There's only one small thing, which is we don't know yet how to find this A prime. Well, I claim it's not very hard. Let's see. Actually, why don't you guys do the hard work? So let's say that I have a plane vector A with two components, A1, A2, and I want to rotate it counterclockwise by 90 degrees. So it looks like maybe we should change some signs somewhere. Maybe we should do something with the components. Can you come up with an idea of what it might be? Okay, so I see a lot of people answering 3. I see some other answers, but the majority vote seems to be number 3, minus A2 and A1. I think I agree. So let's see. Let's say that we have this vector A with components A1, so A1 is here, and A2, so A2 is here. Okay, let's rotate this box by 90 degrees counterclockwise. So this rectangular box ends up there. It's the same box, just flipped on its side. So this length here becomes A1, and this length here becomes A2. And that means our new vector A prime is going to be, well, the first component looks like an A2, but it's pointing to the left when A2 is positive. So actually it's minus A2. And the Y component is going to be the same as this guy, so it's going to be A1. Okay. If you wanted instead to rotate clockwise, then you would do the opposite. You would do A2 minus A1. Okay, is that reasonably clear for everyone? Okay. So, well, let's continue that calculation there. A prime we've decided is minus A2 comma A1. So minus A2, A1, dot product with, let's call B1 and B2 the components of B. Then that will be, well, minus A2 B1 plus A1 B2. Let me write that the other way around. A1 B2 minus A2 B1. And that's a quantity that you may already know under the name of determinant of vectors A and B, which we write symbolically using this notation. So we put A and B next to each other inside a 2x2 table, and we put these vertical bars, and that means the determinant of these numbers. It means this guy times this guy minus this guy times this guy. Okay? So that's called the determinant. And geometrically, what it measures is the area, well, not of a triangle because we didn't divide by 2, but of a parallelogram formed by A and B. So it measures the area of the parallelogram with sides A and B. And of course, if you want the triangle, then you will just divide by 2. Okay, the triangle is half a parallelogram. There's one small catch. The area usually is something that's going to be positive. This guy here has no reason to be positive or negative because, in fact, well, if you compute things, you will see that whether it's positive or negative depends on whether A and B are clockwise or counterclockwise from each other. I mean, the issue that we have, well, when we say the area is 1/2 length A, length B sine theta, that was assuming that theta is positive, that its sign is positive. Otherwise, if theta is negative, maybe we need actually to take the absolute value of this. So just to be more truthful, I will say the determinant is either plus or minus the area. Okay. Any questions about this? Yes?
You're discussing dot product of A, B, what is that?
Oh, sorry, that's not a dot product. That's a usual multiplication. Okay? That's length A times length B times sine theta.
What is that equal?
And so that's equal to the area of a parallelogram. So let me explain that again. So if I have two vectors A and B, so I can form a parallelogram with them, or I can form a triangle, okay? And so the area of a parallelogram is equal to length A, length B, sine theta is equal to the determinant of A and B. While the area of a triangle is 1/2 of that. And again, to be truthful, I should say these things can be positive or negative. So depending on whether you count the angle positively or negatively, you will get either the area or minus the area. The area is actually the absolute value of these quantities. Okay, is that clearer? Okay. Yes, sorry.
You said the determinant could be negative or positive. How do you fix it?
So if you want to compute the area, you will just take the absolute value of a determinant. Okay? So area will be well, I should say the area of a parallelogram so that it's completely clear. Sorry, you have also a question? Yeah. Explain again, sorry, what's the question? How the determinant equals the area of a parallelogram? Okay, so the area of a parallelogram, it's going to be the base times the height, right? So the base, let's take this guy to be the base. So the length of the base will be length of A. Then the height will be obtained by taking B, but only looking at the vertical part. So that will be length of B times the sine of theta. Okay, so that's how I got that the area of a parallelogram is length A, length B, sine theta. And then I did this manipulation and this trick of rotating to find a nice formula. Yes? So you're asking ahead of what I'm going to do in a few minutes. So you're asking about the magnitude of A cross B. So we're going to learn about cross product in a few minutes. And the answer is yes, but cross product is for vectors in space. Here I was simplifying things by doing things just in the plane. Okay, so just bear with me for 5 more minutes and we'll do things in space. Yes? That's correct. The way you compute this in practice is you just do this. Okay, that's how you compute a determinant. Yes? What about? So 3 dimensions we are going to do now. Okay? More questions? Should we move to? Okay, let's move to space.